Mike, and everyone. The title might be a little bit deceiving because the northwest flow doesn't really mean Pacific Northwest. This is something all about Central Plains, Middle West, but it was storms like these happens underneath the so-called northwest flow conditions. Okay? And these are long traveling storms. So you can see storms like that. Pretty exciting. And they come and go, but then they have this persistent track. And they know, it's totally known as derecho or line storms. And the unique part of that is this long lead. You can see the trajectory there. And it happens mostly during middle summer to late summer, say, end of June through maybe September sometimes. And the track like that has a strong impact on agriculture. So you know that. You can see that whatever the windstorm can buy and then cross down in addition to property damage. The turn has been found very early on, and this is just one of the classic study by Johns. You can see that in 1982. So he was able to identify and then compute those frequencies of storm like that under these atypical storm flow conditions, because usually you see a big trough, but now this is the ridge. The trough is actually on the far end. And later on, when they try to compile the frequencies for derechos, and they come up with a very similar frequency map of the two. And the derecho frequency actually peaks in July, okay, or the northwest flow, severe outbreaks. And that is also 1 to 2 months separate from the typical tornado or MCC frequencies in the Central Plains. Okay. So the purpose of this study, and actually the series of studies, is trying to understand what is making these storms so persistent, long-lived, and systematic on their designated track. And we found that it actually is coupled with something in the middle troposphere. This is 600 millibar, so you can see the streamlines and precipitation. This is just another case in late summer. And these, I give it a name, it's a little bit awkward. It's called middle tropospheric perturbation, and then you just call it MP. Why is that? Well, number one, there's nothing above. If you look at 200 millibar, for example, usually you don't see any of the perturbations. It's strictly middle level. The other reason I like to call that is because that is a regulator for storms, just like this gentleman there regulating the storm. So, with the modern data in this case, we use the regional analysis. We could track the storms, track the trough or the perturbations, not tracking the storms, just track the troughs. And then we have, of course, a set of criteria there. And we could actually backtracking into Rocky Mountains. In many cases, actually originate from near the Pacific Northwest Mountains, Northern Rockies there. And you can see that the downstream part of the two indicate that this is the storm, and this is a trough that later generates some sort of storm. Here, this is more like developed storms. But what's surprising, or we consider something newer, is that when you backtrack them to here, they consist of dry vortices sometimes, and that do not necessarily initiate storms. Sometimes they just die prematurely. But a lot of that actually came far to the west. So the idea is that if we can understand a region of that, theoretically you can help forecasting, or like me, I'm doing climate research more. You can understand what climate change or warming has this effect on storms like that. Okay? So this is just to reinforce the importance of troughs like that, perturbations like these. The MPs, if you can track it back to precipitation contribution, or in this case, we use severe gust of wind and hail records, and just to compile the frequency, and they contribute as much as 60, sometimes 70% during the season of July and August on this track. So we want to understand if this is a climatological feature. Why is that? Because when they have these unique and concentrated systematic patterns, they're usually very robust that you can just clearly see them in a climatological view. So we track this back, and what you're seeing, this thin line here is the daily mean of their frequency. So subject them to some grid points, you can construct a frequency like that. And the solid line here is just the frequency corresponding to one time step. Okay, so daily mean is in line. So the disturbances, you can see that at certain time of the day, some place you have more stones, some place you have less stone. So you can plot that for the entire 48 hours. It's actually 24 hours repeating. And if you remove the mean, this is the frequency you can see. So by doing nothing else, simply just projecting them back onto the spatial frequency, and you can track them that they propagate in these systematic manners. The background yellow is shading is climatological vorticity at the middle level. So this is a climatological feature. And we know that there is a propagating precipitation signal in the central plains. And so when combined with that, it appears that you have the MP perturbations formed earlier on in the mountains, and then in the evening, those slope convection develops, and then the two couple, and they start to migrate. So that appears to be the case. More tests to do it. But later on, we found out that if you evaluate central plains, you know that summertime, the forecast skill is not good, even though the synoptic conditions are easier to focus in some way. This is the stationary front, and it's very often apparent in summer times, in midsummer. Okay? And we know from these schematic features that the ratios usually go along this wind direction, that's northwest flow, along this stationary front. Okay? That's the conceptual features. However, if you look at the NAM model, this, you can see that the model tends to generate an elongated frontal band. This is not the average. This is just one time step. So the model is consistently telling you, or it thinks that, oh, I have a stationary front here, therefore I have a red band here. When in reality, we know that even though you have a front, the precipitation is isolated and it's moving. Okay? So models are not capturing that. So we did a study just to focus on precipitation like this when there is a stationary front, and then you start to chop across those grid points, realign it like that, and then we analyzed for probably 4 years of case, and found that, well, indeed, models tend to produce a frontal ram band when in reality the precipitation pattern is an isolated storm and then propagate across the front, but in models they don't do that. Okay? Another challenge in forecasting is that when you subject the forecasting like storms into some objective testing, this ETS score, you can see that, well, in this case, this is observation, focus 1, focus 2, these will have better scores than that, right? But when you, in reality, you know that models actually produce the storm better in focus 1 here. So the hypothesis would be, how does the model do in capturing the perturbations like this? If they have better performance in the perturbation, would the score increase? And how to fix that? This is just two of the cases here. So you can see this is observation, the trough, and then in the prediction here, the trough is behind. The trough is too slow. So we try to pull all these cases and then align their precipitation into their mid location. So they no longer are geographically fixed. Move them around. And we found out that actually this is a model prediction. This is an observation. The model is capturing the trough quite well here, and then the score increase. So here's just some structure showing you that this is indeed a unique type of perturbation systems. Now, they are not a barotropical wave, and they are not MCS as well. They exist
before the storm was generated. So I'm going to quickly go through this genesis mechanism here. Why they say this region is so unique? Well, the number one thing we thought is that we had learned about low-level jet earlier on, that in the Great Plains, this is more like a midnight situation. Low-level jet, return flow in the troposphere, middle troposphere, cross mountain flow. But when it evolved into morning, we know the inertial oscillation rotate them, and at the middle troposphere, they meet, and then they create so-called distraction, so increasing the vorticity there. So this is one of the hypotheses. The other one we see there's another peak in the evening. Okay, these are just some measures for dynamic instability. So what you're seeing is that during 0 hours, that is evening hours, we have the atmosphere conditions is favorable for shorter waves to develop much quicker. Okay, same thing here. And that responds to something we call the Charleston type of instability, which is a measure to say that, okay, if you have unstable waves, short wave developed there, it is likely to grow. And you can see in the early morning, we don't have that. So we also test some models removing mountains. So with mountains, you see that. Without mountains, you don't see that. It tracks cross-section-wise, telling you that without mountains, you don't have the dynamic instability as a result from the observations. So this is just some metaphor. It reminds me to think of the African steady waves. Because in Africa here, we have the thermal low, very strong. And the thermal low creates a very strong dynamic instability in the middle level, okay? Not only the lower level. And that creates these African instabilities. And we thought that actually this metaphor can be applied
for graphics.
Because the same instability really also exists there. You've got this anticyclone, and then you have some wave source in terms of dynamic instability there. You can read all these. And when they couple with low-level jet, and then they form something more for the northwest flow outbreaks. And that happens quite frequently during mid-summer. Okay? And forecast-wise, we have this limitation that the wave is too slow, too weak, and then you tend to generate this frontal band-like situations, which is not really in reality doesn't exist. And we believe that the Pacific Northwest or Northern Mountains is important. I know I'm running out of time, so I'm just quickly going to run through this. This is the temperature difference in terms of change after 1979. You can see that the heating rate from June to July has increased a lot here. What does that have to do with the instability? I actually don't know. This is just a result, and we don't really have the cause and effect relationship. We define that the July MPs have expanded northward, and that seems to affect New York, for example. And in June, this is more robust because more MPs occurring in June means that there's a higher chance for them to couple with the low-level jet and then high moisture contents at that time, and that may lead to recent events. If you look back the news, I mean, the past 3 years during late June season, they all have these events, and each one is stronger than the one in the previous years. That's all. I mean, this little commercial saying some fellowship offering in Utah State, and they pay quite well if you live in Utah, not in Seattle, of course. With that, thank you very much.